Welcome back. This lecture is a continuation of the earlier lecture wherein I introduced centrifugal compressors. In this lecture I shall discuss the performance aspects of centrifugal compressors and briefly discuss the commercial centrifugal machines. Okay. The specific objectives of this particular lecture are to discuss refrigerant capacity of centrifugal compressors and how to control the refrigerant capacity, and discuss the phenomena of surging in centrifugal compressors, discuss the effects of operating temperatures and speed on performance, performance comparison with reciprocating compressors, and finally discuss briefly commercial systems with centrifugal compressors. At the end of this lecture you should be able to explain how the refrigerant capacity of centrifugal compressors can be controlled, explain the phenomena of surging, discuss the effects of operating temperatures and speed on compressor performance, compare the performance with reciprocating compressors, and finally describe commercial systems working with centrifugal compressors. Now let us look at the refrigerant capacity of centrifugal compressors. For a given set of condenser and evaporator temperatures, the required pressure rise across the compressor remains same for all capacities large and small. That means if you fix the evaporator and condenser temperatures, obviously evaporator pressure and condenser pressure are fixed. So the pressure difference between the across the compressor also remains fixed. This is irrespective of the capacity. That means if you have a system working between 0 degrees evaporator temperature and 30 degrees condenser temperature, so whatever be the capacity, whether it is 100 watts or 100 kilowatts, the pressure ratio and the pressure difference remains fixed irrespective of the capacity. This holds good for any type of compressor. Okay, but there is a small problem when it comes to centrifugal compressors. Let us look at that. We have seen that in centrifugal compressors the pressure rise depends on the impeller size, number of impellers and rotational speed of the impeller. Since these parameters must remain same for compressors of all capacities operating between the same temperatures. Okay, let me explain this. Okay, so this is the picture I have shown you in the last lecture. We have the velocity diagram here, and as I have explained, you have this U2 is your tip speed. This is the tip speed, and I have defined all these things, and in fact these things are again repeated here. VT2 is the tangential component of refrigerant at the exit of the compressor, Vn2 is the normal component, and Vr2 is the relative velocity, and V2 is the absolute velocity. Okay, this is what we have discussed in the last class, and from by assuming that the inlet is axial, we have got these expressions. For example, for an axial inlet, that means there is no tangential component at the inlet to the compressor. We found that the work input or power input to the compressor is given by this expression, where m dot is the mass flow rate, U2 is the tip speed, and Vt2 is the tangential velocity. And from the velocity diagram, what we have done is we have replaced this Vt2 and we have written this in terms of the tip speed U2 and the normal component Vn2 and the blade angle beta. Okay, and then we have extended this and we have derived the equation for an impeller having radial curved blades, and in fact I have explained in the last class that for radial curved blades the angle beta is equal to 90 degrees. Okay, so once the angle beta becomes 90 degrees, you can see that the power input is equal to m dot into U2 square, or the specific power input or specific compressor work is simply equal to U2 square. Okay, and for isentropic compression with radial blades, we have derived this equation, which gives the ratio of this exit pressure to the inlet pressure as a function of the inlet parameters Pi Vi, isentropic coefficient K, and the tip speed omega into R2 square. And in fact in the last class I have explained that when you fix the inlet condition, that means Pi and Vi are fixed, and if you also assume that K is constant, you can see that the pressure ratio is purely a function of your tip speed of the impeller. That means tip speed in turn depends upon the rotational speed omega and the outer radius R2. Okay, that means from this expression you see that once you fix the pressure difference or the pressure ratio, then the required tip speed gets fixed irrespective of the capacity. Capacity does not come into picture. Okay, this is the typical characteristic of a centrifugal compressor. Let us see what is the consequence of this. That is what is mentioned here. So if you want to design a refrigerant system for a lower capacity, what is that we have to do? First of all, let us look at the expression for mass flow rate. The mass flow rate of refrigerant is given by this expression, where m is the mass flow rate, and this is equal to Vn2 into AFP divided by V2, where Vn2, as I have already explained, is the normal component of refrigerant velocity at the exit of the impeller, and AFP is the peripheral flow area, okay, and small v2 is the specific volume of the refrigerant at the exit. So you can see that the mass flow rate depends upon the normal component, area of cross section at the periphery, and the specific volume. Suppose you are fixing the conditions at the exit, then the specific volume v2 gets fixed, okay. Then mass flow rate depends only on the normal velocity and also on the peripheral flow area, okay. The ratio of the normal velocity to the tip speed is sometimes called as a flow coefficient, okay, and this flow coefficient is normally obtained from measurements. Once you say that the flow coefficient is this, and if you know the tip speed, then you can calculate what is the normal component of velocity, okay, and when if you know the flow area, then you can calculate the mass flow rate, right. Now let us see how the capacity has to be reduced. Now for a given blade diameter, the flow area at the periphery depends on the number of blades and the width of the blade, okay. And if the number of blades are fixed, then to design the compressor for smaller refrigerant capacity, one has to reduce the width of the impeller. What do we mean by designing the refrigerant system for smaller capacities? When everything else is fixed, the smaller capacity means smaller mass flow rate, okay. So if you have to design the system for a smaller refrigerant capacity, you have to reduce the mass flow rate of refrigerant, okay. And from this expression you see that if you have to reduce the mass flow rate of refrigerant, either you have to reduce the normal velocity at the exit, or you have to reduce the flow area, okay. Now let us look at the flow area. Flow area depends on what? For a given impeller diameter, the flow area depends upon the number of blades. It is less sensitive to the number of blades, but it is it mainly depends on the width of the blade. So if you want to reduce the flow area, you have to reduce the width of the blade, okay. Let me show the blade from the side view. So this is the impeller, and this is the shaft, and it is rotating, let us say, in this direction. So this is the width of the blade, okay, width of the impeller W, okay, and these are the impeller blades, as I have shown all these things. So if you want to reduce the flow area, you have to reduce this W. That means these things become narrower, okay. Now what is the problem if you reduce the width? You find that as the width of the impeller is reduced, frictional losses increase, leading to lower efficiency. That means when you are forcing the refrigerant to flow through a narrow passage, obviously frictional losses increase, okay. So if you are trying to design a system for the same for a small refrigeration capacity, you have to keep the tip speed constant. If you are keeping the rotational speed constant, that means that the diameter of the impeller is fixed. So only option left for you is to reduce the, of course it is not the only option, but one option left for you is to reduce the width, and we have seen that as you reduce the width, the frictional losses increase. Once the frictional losses increase, the efficiency of the compressor comes down, okay. So this is one of the problems in reducing the capacity of a centrifugal compressor, okay. Now let us look at other options. What are the other options? An alternative is to reduce both diameter and width of the impeller simultaneously, so that the normal component of velocity and frictional losses can be reduced, okay. So if you want to reduce the frictional losses, what you have to do is you have to reduce the length of travel, okay. One way of reducing the frictional loss is to reduce the length of travel. That means you have to reduce the diameter of the impeller, okay. That means you have to simultaneously reduce the diameter of the impeller and width of the impeller, so that the mass flow rate gets reduced, okay. But what is the problem with this? Once you reduce the diameter of the impeller, and if you are keeping the rotational speed constant, then your tip speed reduces. Once the tip speed is reduced, the pressure rise across the impeller reduces, okay. Since the total required pressure rise remains constant, and the pressure rise across a single impeller reduces, you have to go for multi-stage compressors, okay. That means more number of impellers. This is the problem with this method, okay. So that is what is summarized here. Since this reduces the pressure rise across a single impeller, one has to increase the number of stages. What is the problem of increasing number of stages? If you increase the number of stages, the manufacturing cost increases. That means the initial cost also goes up, okay. So this is the disadvantage with this method. Thus you find that for a centrifugal compressor, a lower limit is there on the refrigerant capacity of on the refrigerant capacity. Okay. And in practice, the lower volumetric flow rate is limited to about 0.7 meter cube per second, and the minimum refrigeration capacities are around 300 kilowatt for air conditioning application. That means you cannot really have a centrifugal compressor for, let us say, 5 kilowatt or 10 kilowatt or something like that, because that becomes too inefficient. It's not that you cannot design it, but the compressor will be very, very inefficient. Okay, so if you want to have good efficiency, you must maintain certain things at a minimum level, then the capacity automatically, the lower limit gets automatically fixed. Okay, so that is the reason why centrifugal compressors are normally used for high capacity applications. Okay. Since our compressor works more efficiently at higher volumetric flow rates, refrigerants having lower densities, that means higher normal boiling points such as R11 are ideal refrigerants for centrifugal compressors. So if you want to have, see the when you are fixing the tip speed, or when you are fixing the by fixing the tip speed, you are fixing the, let us say, the normal component. Okay, that means you are fixing the volumetric capacity. Okay, so the mass flow rate is nothing but the product of volumetric capacity and the density. Okay, if the density is less, for the same volumetric capacity, you can volumetric flow rate, you can have less refrigerant flow rate. Okay, so for centrifugal compressors, if the volumetric flow rate is large, then you can go for wider impellers. That means you can reduce the friction losses. Okay, so ideally we would like to have as high a volumetric flow rate as possible. At the same time, you would like to have refrigerant capacity small. This is possible only when the density of refrigerant at the impeller exit is small. Okay, that means the pressure should be small. This is typically possible with refrigerants having high normal boiling point. Okay, one typical example is R11. R11 has a boiling point of about 24 degrees centigrade. That means its density will be very low. Even at 40 degrees or 50 degrees centigrade. Okay, so it's an ideal refrigerant as far as centrifugal compressors are concerned. That is the reason why R11 was very widely used in all centrifugal compressor based air conditioning systems. Okay, however, unfortunately R11 was banned due to its high ODP. Okay, so now you can't have R11. Of course, it doesn't mean that you cannot have or you don't have centrifugal compressors working with a wide variety of refrigerant. They are available. Okay, but of course some of them are better than the others. Okay. So as I said, centrifugal compressors in larger capacities are available for a wide range of refrigerants, both synthetic as well as natural. Now let us look at capacity control. How do we control the capacity? The capacity of a centrifugal compressor is normally controlled by adjusting inlet guide vanes. In fact, in the last class I have explained what do we mean by inlet guide vanes, and I have also mentioned that these are mainly used for controlling the capacity. So let us look at this. Okay, so this is this figure I have shown in the last lecture. So as I have already mentioned, these are the inlet guide vanes, and through which the refrigerant enters. Okay, then it takes a 90-degree turn and flows through the impeller. Okay, so when you have the guide vanes here, by adjusting the guide vanes, what you can do is you can introduce a tangential component at the inlet. Okay, in our analysis we assumed that the tangential component is 0, and we have that means the refrigerant enters axially at the inlet. Okay, and that's how we calculated the pressure rise and specific work input and all that. Okay, but it is possible to introduce a tangential component by adjusting the inlet guide vanes. What happens when you adjust the inlet guide vanes? As I said, it introduces a tangential component, and once you introduce a tangential component, the pressure rise across the impeller, the mass flow rate, everything changes. Okay, so you can control all these parameters by controlling the angle at which the guide vanes are kept inside the inlet. Okay, this is one very popular way of controlling the capacity of centrifugal compressors. Now let me show typical performance curves at different inlet guide vane angles. Okay, so this figure shows the pressure ratio, okay, versus flow rate for different inlet guide vane angles. You can see that the angle is given as 90 degrees, it varies from 90 degrees to 0 degrees. When you say 90 degrees, that means the inlet guide vanes are fully open. Okay, at this condition you get the maximum capacity. For example, if I am fixing the, let us say, the pressure ratio, okay, pressure ratio is fixed at this point, let us say, then you can see that as you are increasing the angle, you are getting higher flow rate. Higher flow rate means higher capacity. Okay. So, as you are reducing the angle, that means as you are closing the guide vanes, the flow rate is getting reduced, while the pressure ratio is staying constant. Okay. So, that is how you can control the capacity. And as I said, this is a very popular method of controlling the capacity, and here you can see that there is a surge line. Okay, I will explain what is surging in this class. Normally the performance is not shown beyond the surge line. Okay. So, as I have already mentioned, the adjusting of inlet guide vanes provides a swirl at the impeller inlet and introduces a tangential velocity at the inlet, which gives rise to different flow rates. This method is efficient as long as the angle of rotation is high, i.e. the vanes are near the fully open condition. Okay, it is not that it is a very efficient method under all conditions. The method of controlling the capacity by adjusting the inlet guide vanes is good as long as you are not closing the guide vanes too much. That means it is staying near the fully open condition. That means the angle is close to 90 degrees, not to 0 degrees. Okay, and if you are trying to reduce the capacity too much by closing the inlet guide vanes too much, that means when your angle is closer to 0, that means the inlet guide vanes will be simply acting as throttling devices. Okay, there will be simply pressure reduction across the guide vanes, and then the method becomes inefficient. Okay, so if you want to use this method, you should use it within certain limits so that you do not close the vanes too much. Okay. Capacity control is also possible by adjusting the width of the vaneless diffuser or by adjusting the guide vanes of vane diffuser. In the last class I have explained what is the function of a diffuser, and I have already also mentioned that you can have either a vane diffuser or a vaneless diffuser. Okay, and by adjusting the width of the vaneless diffuser or by the orientation of the vane diffuser, you can control the flow rate. Normally you do not use it alone. Normally the method of capacity control by the vane diffuser is clubbed with the method of capacity control by the inlet guide vanes. Okay, so they are used in combination. So, using a combination of the inlet guide vanes and diffusers, the capacities can be varied smoothly from 10% to 100% of the full load capacity. Okay, so you can get a very wide range of capacities by these methods. Capacity can also be controlled by varying the compressor speed using gear drives. For the same pressure rise, operating at lower speeds reduces the flow rate, thereby reducing the refrigeration capacity. Of course, keeping everything constant, if you reduce the speed, then obviously all the velocities will get reduced, so the flow rate automatically gets reduced. Okay, so this is another good method of controlling the capacity. That means you are varying the speed. Okay, of course, when you are varying the speed, it may also affect the pressure rise. Okay, so it's not that you can vary it over any range. Okay, within certain range you can vary it, right. So, to sum up, the most important methods of capacity control as far as centrifugal compressors are concerned are adjusting the inlet guide vanes and adjusting inlet guide vanes plus adjusting the diffuser or speed control. Okay. Now, let us look at performance aspects of centrifugal compressors. The relationship between pressure and volume is a straight line in the absence of any losses. That means, for an ideal centrifugal compressor, if you plot the pressure rise versus the flow rate, you find that you get a straight line. That means, I will show you that as the flow rate increases, the pressure rise reduces, or as the flow rate reduces, the pressure rise increases. This characteristic is typical of any dynamic machine such as centrifugal pumps or centrifugal compressors. Okay. So, let me show the characteristics. Okay, you can see I have plotted pressure, that means the exit pressure versus the volume. Okay. So, as I was mentioning, this is the performance curve, this curve without any losses, that means that of an ideal centrifugal compressor. Here you can see that for the ideal centrifugal compressor, the performance curve is a straight line. Okay, and you can see as the volume is reducing, pressure is as the volume is increasing, sorry, the pressure is reducing, and as the volume increases, the pressure increases. Okay. Now, in actual compressors there are several losses. So, if you include the losses, how does the performance characteristic look like? For example, what are the losses in a centrifugal compressor? I have explained in the last class. One loss is the eddy loss. Okay, and I have explained in the last class that the eddy loss is because of your secondary flows. Okay, the Coriolis acceleration component, and due to the secondary flows you have eddy losses, and this eddy loss also almost varies linearly. So, when you include this eddy loss, the head reduces. Okay, so this is the curve which includes the head losses. I mean, I am sorry, includes the frictional losses. So, the only next loss is to be considered is the frictional loss. If you are considering the frictional losses do not vary linearly, but they vary as a power of volume or as a power of velocity. So, you can see that as the volumetric flow rate is increasing, the frictional pressure losses are increasing. So, when you include eddy loss as well as frictional loss, you find that the head developed or the pressure gets reduced further. So, for example, let us say that this is a volume at which I am trying to find out the pressure. So, without any losses, this is the pressure rise. Okay, this is the ideal pressure rise. So, if you are including eddy losses, this will be the pressure developed, and if you are including the frictional losses, this will be the pressure developed. So, the pressure developed gets reduced because of the losses. Finally, if you also include the shock losses at the inlet, this will be the resulting curve. Okay, so finally the curve resulting curve is this. Okay, so an ideal curve is a straight line like this, but the resulting curve initially the pressure increases initially with volume, and it reaches a peak and then again reduces. Okay, and as I said, the three major losses are shock losses, friction losses, and eddy losses. Okay, and normally this is a point called as a design point. How do you fix a design point? Design point is normally fixed in such a way that at that point the total losses are minimum. Okay, you would like to operate the system always at the highest efficiency. Okay, that means where the losses are minimal. That's how the design point is fixed. Okay. So, as I have already mentioned, if you in actual compressors, losses occur due to eddy formation in the flow passages, frictional losses, and shock losses at the inlet to the impeller. And the shock losses or entry losses are due to change of direction of refrigerant at the inlet and also due to pre-rotation. These losses can be controlled to some extent using the inlet guide vanes. So, I have explained the meaning of eddy losses in the last class, and I have also explained the meaning of frictional losses, okay, due to viscous shear. So, I did not explain what is an inlet loss. Okay, the inlet loss mainly happens because as soon as the refrigerant enters into the impeller through the inlet, it has to take a 90-degree turn. That means there is a sudden change in the direction. Okay, whenever there is a sudden change in the direction of the fluid as it is flowing, there will be losses. Okay, this is one of the reasons for the inlet losses. Apart from that, when you have the inlet guide vanes, they also introduce some losses. Okay, so mainly the inlet losses are as a result of the directional change and due to the presence of the guide vanes. Okay, of course you can minimize them by adjusting the guide vanes properly. Okay, this I have already explained. Now, before we go to other performance characteristic curves, I would like to explain an important phenomena called surging. Okay, what do we mean by surging? This is very, very important in the centrifugal compressors. So, let me explain this. A centrifugal compressor is designed to operate between a given evaporator and condenser pressures. Due to variation either in the heat sink or refrigerated space, the actual evaporator and condenser pressures can be different from their design values. For example, if the condenser pressure exceeds the design discharge pressure of the compressor, then refrigerant flow reduces and finally stops. Okay, so let me explain this. Normally, whenever you design a system, you always design it for a design condenser and evaporator temperatures or pressures. Okay, you can fix the temperature, then automatically pressure gets fixed. Okay, whether it is a reciprocating compressor or a centrifugal compressor. So, since we are discussing centrifugal compressor, let us specifically discuss what is the problem with centrifugal compressors. Okay. So, when you design a centrifugal compressor for a fixed evaporator and condenser temperature, and you choose the impeller speed, impeller diameter and the width of the impeller and all that, right, based on the design points. Now it is not necessary that the evaporator temperature and condenser temperature have to stay always at the same design conditions. Okay, either evaporator temperature can reduce or increase, or the condenser temperature can also increase or reduce depending upon the conditions. Okay, the evaporator temperature can reduce when the load is falling, that means the refrigeration load is falling, or it can increase when the refrigeration load is increasing. Similarly, the condenser temperature can increase when the heat sink temperature is increasing, or the heat transfer rate on the heat in the condenser is reducing. Okay, so due to these reasons, there are many many possibilities where the system will be working at off design conditions. Okay, that means the pressure ratio or the pressure difference will be different from the design pressure difference. Okay, when the system is operating at off design conditions, you will find that the centrifugal compressor behaves in a different manner compared to a reciprocating compressor. Okay, let me give an example of the variation of condenser temperature. Let us say that the heat sink temperature has increased. Okay, and as you know, the heat sink normally depends upon the ambient conditions. Okay, if the ambient temperature goes up, let us say in summer, then heat sink temperature increases. Once heat sink temperature increases, since the condenser is fixed, the condenser temperature increases, condenser pressure also increases. Okay, so the actual condenser pressure will be higher than the design condenser pressure. Once this is higher than the design condenser pressure, you find that the centrifugal compressor will find it increasingly difficult to maintain the same flow rate. Okay, so as soon as the condenser pressure starts going beyond the design condenser pressure for a given evaporator pressure, the flow rate starts reducing. Okay, and a point will come at which the flow rate completely stops, and any further rise in condenser, the flow actually reverses. That means instead of flowing from the evaporator to the condenser, the flow will take place from the condenser to the evaporator. Okay, so reversal of flow takes place when the condenser goes beyond a certain value. Okay, let us see what happens because of this. So as I said, further increase in condenser pressure causes a reverse flow of refrigerant from condenser to evaporator through the compressor. You understand clearly that why this happens. This happens because unlike reciprocating compressor, in a centrifugal compressor the pressure rise is almost fixed when you are fixing the tip speed. Okay, that is what we have discussed and that is what we have seen from the equations. Okay, so as long as you are running the compressor at the same speed, since the diameter is already fixed, that means the pressure developed across the impeller remains same. So it cannot increase just because the condenser pressure is increasing. Okay, so the pressure developed remains mainly a function of the tip speed. So if you are keeping the tip speed constant, pressure developed also remains constant. Okay, since it cannot develop a pressure higher than the condenser pressure, then obviously due to the pressure gradient, the flow will take place in the reverse direction. That means hot refrigerant from the condenser enters the evaporator through the compressor. Okay, since you don't have any valves or anything, it can freely flow through the compressor and it can go to the evaporator. Okay. Now if you compare this with what happens in reciprocating compressor, what happens in a reciprocating compressor when the condenser pressure is increased? So if you remember the working principle of a reciprocating compressor, in reciprocating compressor we have suction and discharge valves. Okay, so when the condenser pressure is increasing, the discharge valve will not open. Okay, so what happens is the pressure inside the cylinder also has to increase. Okay, that means that opening of the discharge valve is delayed due to higher condenser pressure. Okay, and only when the pressure inside the cylinder goes beyond the condenser pressure, then the discharge valve opens and the flow takes place in the normal direction. There is no way flow reversal can take place, because as long as the discharge valve is closed, flow cannot take place from the condenser to the evaporator. Okay, because you have the valves there, whereas in a centrifugal compressor we don't have any valves. Okay, so reversal of flow can always take place, and since this is not a positive displacement type of machine, it cannot go on pumping even though the pressure is increasing. Okay, so to put it simply, a reciprocating compressor can work or can go on compressing the refrigerant and go on pumping the refrigerant at a lower efficiencies, but it can still pump a finite amount of refrigerant, okay, in the normal direction, whereas a centrifugal compressor beyond a certain point it cannot simply pump the refrigerant. Okay, so it will stop pumping and in fact the reversal of flow takes place. Okay, this is a typical characteristic of a dynamic machine. Now what is the problem because of this? As a result of this, the evaporator pressure increases. Now what happens when reversal of flow takes place and hot refrigerant from the condenser enters into the evaporator? That means you are adding load to the evaporator artificially, right? That means the load on the evaporator increases. Once the load on the evaporator increases, evaporator temperature increases. Once the evaporator temperature increases, evaporator pressure increases. Once the evaporator pressure increases, the pressure difference across the evaporator and condenser reduces. Okay, once it reduces, the centrifugal compressor can now again pump in the normal direction. Okay, so pumping starts to take place again in the normal direction. Okay, so again refrigerant flows from the evaporator to the condenser. Once refrigerant starts flowing from the evaporator to condenser, again the evaporator pressure drops. Okay, again the pressure difference increases. Once the pressure difference increases, again the compressor will find it difficult to pump in the normal direction. Reversal of flow takes place, and again this cycle continues. Okay, this phenomena is known as surging, right? Okay, so as I said, once the refrigerant starts flowing in the normal direction, the pressure difference increases, and again the reversal of flow takes place, and the process repeats. This oscillation of refrigerant flow and the resulting rapid variation in pressure difference gives rise to the phenomena called surging. Surging produces noise and imposes severe stresses on the bearings of the compressor and motor, ultimately leading to their damage. Okay, so because of surging, you find that there is an oscillation of refrigerant flow from evaporator to condenser and then condenser to evaporator. So there is a rapid oscillation and there is a rapid variation of pressures. Okay, due to these rapid changes, very objectionable noise is produced. Okay, that is not the only effect. Since the pressure variation is very rapid, there will be severe stresses on the bearings of the motor and on the compressor. Ultimately, if nothing is done, the motor and compressor get damaged. Okay, so this is a very important problem which has to be taken care in actual systems. So continuous surging is highly undesirable, even though it may be tolerated if it occurs occasionally. Now as I have already explained, it must be clear to you that surging is most likely to occur when the refrigeration load is low and or the condensing temperature is high. Okay, so surging takes place when the pressure difference across the compressor is high. So when the pressure difference will be high, either the condensing temperature pressure is high or the evaporator pressure is low. Okay, evaporator pressure will be low when the load is low. Okay, so you find that surging will normally occur when the heat sink temperature is very high and refrigeration load is low. Okay, so this is the most favorable condition for surging. In some centrifugal compressors, surging is taken care of by bypassing a part of the refrigerant from the discharge side to the evaporator, thereby increasing the load artificially. Okay, so something like hot gas bypass is done, so that you artificially increase the evaporator capacity. That means you increase the evaporator pressure and reduce the pressure difference and avoid surging. Thus, a centrifugal compressor cannot pump the refrigerant when the condensing pressure exceeds a certain value and or when the evaporator pressure falls below a certain point, unlike reciprocating compressors. I have explained this already. Now let us look at the effects of evaporator and condenser temperatures. Let us see how, when you vary them, what happens to the compressor performance. Okay. So here I have plotted condensing temperature in this curve as on x-axis and load or the refrigeration capacity on the y-axis. And for comparison, I have shown the performance of a reciprocating compressor also here. If you look at the reciprocating compressor, we have seen that as the condensing temperature increases, the refrigeration capacity of reciprocating compressor reduces. Okay, because this will reduce the volumetric efficiency, so the mass flow rate gets reduced and the refrigeration effect also gets reduced slightly. As a result, the capacity reduces. So this curve is for the reciprocating compressor. Now what happens to the centrifugal compressor? You find that up to a certain point, just like reciprocating compressor, for this centrifugal compressor also refrigeration capacity reduces as condensing temperature is increased up to a certain point, and this is more or less linear, and in fact the variation is not too much. Okay, so this is almost similar to a reciprocating compressor, but you find that beyond a certain point there is a sudden drop in the capacity of the centrifugal compressor. This sudden drop takes place because of the problem that we have discussed just now, as because of surging and the related phenomena. Okay, so up to a certain point centrifugal compressor works normally, but beyond that point the capacity reduces drastically. Okay, so normally the centrifugal compressors are operated towards left of this point. where the sudden drop takes place, and normally this will be the some kind of a design point. Okay. And this figure shows the effect of evaporator temperature on the load. Okay. Here again for comparison I have shown the reciprocating compressor performance and the centrifugal compressor. If you look at the reciprocating compressor, you find that as evaporator temperature is reduced, the refrigerant capacity reduces rapidly. Okay. You know that this is because of the reason that as you are reducing the evaporator temperature for a given condensing temperature, the volumetric efficiency reduces and the refrigeration effect also reduces. As a result, the refrigerant capacity reduces. Okay. But it is more or less monotonous, it reduces monotonously. Okay. But if you look at centrifugal compressor, you find that up to this point, as you reduce the evaporator temperature, the reduction in capacity, okay, there is a reduction in capacity with reduction in evaporator temperature, but this reduction capacity is not much. Okay. But beyond this point, you find that when the evaporator temperature is reduced further, there is a sudden drop in the capacity. Again, this is also linked to your problem of surging and the related phenomena. Okay. So, the from this, so you find that as long as you operate the system to the left of the condensing temperature curve or to the right of the evaporator temperature, this thing, your performance of the centrifugal compressor is good. But once you exceed, once you go beyond these points, you find that there is a sudden drop in the capacity. Okay. So, you should never operate the systems at under these conditions. Okay. One more thing you can notice here is, for example, look at the effect of the evaporator temperature. When you look at the effect of the evaporator temperature, you find that compared to the centrifugal, compared to the reciprocating compressor, the effect of evaporator temperature is more severe on reciprocating compressors. Okay. That means for a given change in the refrigerant capacity, the change in evaporator temperature is less for the centrifugal compressors. So, that is what is mentioned here. Beyond a certain condenser pressure and below a certain evaporator pressure, the refrigerant capacity of centrifugal compressor decreases rapidly, unlike reciprocating compressors where the capacity drop under these conditions is more gradual. However, one advantage with centrifugal compressor is that when operated away from the surge point, the reduction in evaporator temperature with refrigeration load is much smaller compared to the reciprocating compressor. That means you find that centrifugal compressors, when they are operated in the design range, even if the capacity varies, the evaporator temperature does not vary too much. This is an advantage. Okay. For example, when the capacity is reduced and if the evaporator temperature also reduced very much, then you can have problems of freezing of water. For example, if you are using it for water cooling, then evaporator temperature can become so low that the external fluid may freeze, or you may have very low humidities on the external fluid side. Okay, because the large variation in the evaporator temperature. But in case of centrifugal compressor, you find that the variation in evaporator temperature is less for a given variation in the capacity. Okay. Now let us look at the effect of power input. Effect on power input. What happens when you increase the condensing temperature to power input. Okay. Again, you can see here that I have plotted condensing temperature versus compressor power, and we have seen that for reciprocating compressor, the power input increases. Okay, you can see that this is for the reciprocating compressor. The power input increases as the condensing temperature is increasing. Okay, that means W increases as TC is increasing for reciprocating compressor. But you find that for the centrifugal compressor, as the condensing temperature is increasing, the power input is reducing. Why the power input reduces as the condensing temperature is increasing? As the condensing temperature increases, the refrigerant capacity reduces because the mass flow rate reduces. Okay. So, the reduction in mass flow rate is much larger than the increase in the specific work of compression. As a result, the required power input reduces as the condensing temperature increases in case of centrifugal compressors. Of course, this is an advantage because you do not have the problem of motor overloading at under high condensing temperatures. Okay. Whereas this possibility is there in reciprocating compressor. When the condensing temperature is very, very high, the compressor may get overloaded. Okay. But you do not have the overloading problem in centrifugal compressors. As I said, this is due to the rapid drop in refrigerant capacity of centrifugal compressor with condensing temperatures. This characteristic implies that the problem of compressor overloading at high condensing temperatures does not exist in case of centrifugal compressors. The performance of centrifugal compressor is more sensitive to compressor speed compared to reciprocating compressors. You find that again this is I have varied speed, okay, x axis is speed, and in this particular curve the y axis is the percentage of refrigerant capacity and this is the percentage of power input, and this curve is for the reciprocating compressor as you have seen, as I have written here, and this curve is for the centrifugal compressor. You can see that the reduction in the refrigeration capacity with reduction in percentage speed is more gradual in case of reciprocating compressor. Okay, so this is the 100% speed, and let us say that this is 0% speed, and this is 100% capacity. Okay, so similarly this is 100% speed, this is 100% capacity. Okay, so as you are reducing the speed, the refrigerant capacity is reducing almost like a straight line, but for centrifugal compressor you find that the reduction is much rapid. Okay, so for a given change in the percentage speed, drop in refrigerant capacity for centrifugal compressor is much higher compared to reciprocating compressor. And the characteristics of the centrifugal compressor and reciprocating compressor in terms of power input can be seen from this figure. Again you can see that the performance of centrifugal compressor is more sensitive to reduction in speed. Okay, this should be percentage reduction in speed, right. Normally performance of centrifugal compressors are represented by figures that show the performance at various efficiencies and speed. Let me show a typical performance curve which is very useful. This is a typical performance curve of a typical centrifugal compressor, and normally the flow rate is shown on the x axis and the pressure ratio, that is the discharge pressure to the suction pressure, is shown on the y axis, and here the performance is shown for different iso efficiency lines. Okay, so these lines are constant efficiency lines, this one, okay, all these lines are constant efficiency lines, and the innermost one, as you can see here, is the high efficiency line. This is the high efficiency line. Okay, so then this is for the low efficiency. Okay, as you move away the efficiency reduces, and on the same curve you can also see the constant speed lines. Okay, for example these are low speed line and these are all the constant speed lines. Okay, so using this figure, and normally the performance is not shown beyond the surge line. Okay, so you can see the surge line here. Okay, because you do not want to operate the system in the surging zone. Okay, so normally performance is not shown in the surge region. So this figure is very useful. For example, you want to find out at a particular, let us say that at a particular flow rate, okay, and you know the pressure ratio, then you can find out what will be the efficiency that you can expect and what is the required speed. Okay, right. That means given any two parameters you can find out the other parameters using these curves. Okay, they are very useful performance curves. Okay, so these I have already explained. Now let us briefly look at commercial refrigerant systems with centrifugal compressors. Centrifugal compressors are available for a wide variety of applications using a wide variety of refrigerants. Okay, and let me show some of the specifications of commercial machines. Normally systems are available for evaporative temperatures varying from -100 degrees to +10 degrees centigrade, very large variation, and the systems are available for evaporator pressures varying from 14 kPa kilopascal to about 700 kilopascal, and the discharge pressures can vary up to 2000 kilopascals, and the rotational speeds can vary anywhere between 1800 rpm to 90,000 rpm. Normally very high speeds are obtained by using gear drives. Okay, and the refrigerant capacity can vary from 300 kilowatts to 30,000 kilowatts. Okay, so you can see that normally these are used for high capacity applications. And what is the limitation on the, this I have already explained, but let me once again repeat. What is the limitation on the lower side of the capacity, and what is the limitation on the higher side of the capacity? On the lower side the capacity is limited by the impeller width and tip speeds, and on the higher side the capacity is limited by the physical size. Okay, these two constraints put a limit on the available capacities of the commercial systems. Okay. Right now, as I said, for air conditioning application, the minimum capacity available is about 300 kilowatts. Okay, as well as the maximum capacity is about 30 megawatt. Okay, and normally the maximum impeller diameter is limited to about 2 meters, because I have already explained in the last class, as the impeller size becomes large, the tip speed becomes large, so there will be severe stresses at the root of the impeller. Okay, so structurally it becomes very difficult to design it. Since the performance of centrifugal compressor is more sensitive to evaporator and condensing temperatures compared to a reciprocating compressor, it is essential to reduce the pressure drops when a centrifugal compressor is used in commercial systems. Okay. So, the design strategy has got to be different for the refrigerant system when you are using a centrifugal compressor and when you are using a reciprocating compressor. Centrifugal compressor is more sensitive to pressure drops. We have seen just now it cannot handle when the pressure rise goes beyond the design pressure rise. So, you have to minimize the pressure drops. Okay. So, you have to design the system in such a way that the pressure drops in the lines or across any valves or anything is minimal. Okay. And commercial refrigerant systems using centrifugal compressors normally incorporate flash intercoolers to improve the system performance. I have explained this in when we were discussing multi-stage refrigerant systems, what is the meaning of a flash intercooler and what is the purpose of that. Normally when you use centrifugal compressors in commercial systems, flash intercoolers are used for improving the efficiency of the overall efficiency of the system. And the incorporation of flash intercooler is much easier in centrifugal compressors, because normally most of the centrifugal compressors are multi-stage. That means more number of a large number of impellers will be there, and the pressure across each impeller will be gradually increasing, right. So, when you have a flash intercooler, all that you have to do is the exit of the flash intercooler can be connected to an intermediate point, right. You do not have to have a separate compressor unlike in reciprocating compressors. Okay. That is the reason why this is quite popular in centrifugal compressors. Since the compressor is normally multi-stage, use of flash intercooler is relatively easy in case of centrifugal compressors. Commercially, both hermetic as well as open type compressors are available. Open type compressors are driven by electric motors, internal combustion engines using a wide variety of fuels, or even steam turbines. Okay. Normally the smaller capacity systems are hermetic systems, whereas the large capacity centrifugal systems are open type. Okay. So, when you have an open type of compressor, you can use any kind of a drive. Okay. You can use an internal combustion engine, or you can use an electrical motor, or you can even use a steam turbine. Okay. Centrifugal compressors are normally lubricated using an oil pump. You also require lubrication here. Normally in large systems an oil pump is used, that means you have force feed lubrication, and this oil pump can be driven directly by the compressor rotor or by an external motor. The lubrication system consists of the oil pump, oil reservoir and an oil cooler. The components requiring lubrication are the main bearings, a thrust bearing and the shaft fields. These are the components which require lubrication. Okay. A thrust bearing is used because if you look at a multi-stage centrifugal compressor, you find that with the number of the stages the pressure will be increasing, right. That means there is a imbalance, the final stage the pressure will be much high compared to the first stage. Okay. So, there is pressure force acting in a particular direction. So, if you want to balance it, normally they use what is known as the balancing discs. Okay, to statically and dynamically balance the compressor. So, you require lubrication where you put the balancing disc also. However, compared to reciprocating compressors, the lubrication for centrifugal compressors is simplified, as very little lubricating oil comes in direct contact with the refrigerant. So, you find that the design of lubricant system is not as complicated as in case of reciprocating compressors, because normally they do not get mixed in case of centrifugal compressors. Okay, so this with this I complete my lecture on centrifugal compressors. So, let me work out a simple problem on centrifugal compressors. Okay. So, the problem is like this: a two-stage centrifugal compressor operating at 3000 rpm is to compress refrigerant R134a from an evaporator temperature of 0 degree centigrade to a condensing temperature of 32 degree centigrade. Okay. If the impeller diameters of both stages have to be same, what is the diameter of the impeller? Assume the suction condition to be dry saturated, compression process to be isentropic, the impeller blades to be radial, and refrigerant enters the impeller axially. So here let us look at the given information. Okay, the information given is like this: refrigerant is R134A, evaporator temperature is 0 degree centigrade, condensing temperature is 32 degree centigrade, inlet condition to the compressor is dry saturated, compression process is isentropic, number of stages are 2, rotational speed is 3000 rpm, impeller blades are radial, tangential velocity at inlet is 0 meter per second, that means the refrigerant enters axially, and the impeller diameter is same for both the stages. So this is the information given, and from this information we have to find out what is the required diameter of the impeller. This, as I said, is a simple problem. So first let us look at the refrigerant property data. Then you have to find out the property data from R134A properties, and it is mentioned that evaporator temperature is 0 degree centigrade and it is dry saturated, inlet is dry saturated. Okay, so you can find out what is the enthalpy of saturated vapor at 0 degree centigrade, and from the property data you find that this is 398.6 kilojoule per kg. Okay. And enthalpy at compressor exit, we know the compressor condenser temperature, that means we know what is the exit pressure, and we also know the exit entropy because this is an isentropic process. So at the exit condition we know the pressure and entropy, and as you know the exit condition lies in the superheated region. So from the superheated property tables, from the known values of pressure and entropy, you can find out the other properties. Okay, and you find that for pressure corresponding to 32 degree centigrade condensing temperature, and entropy corresponding to the dry refrigerant vapor at 0 degree centigrade, the enthalpy at the exit of the compressor is found to be 419.8 kilojoule per kg. And since the blades are radial with no tangential velocity component at inlet, the enthalpy rise across each stage delta H1 is the enthalpy rise across stage 1. This is equal to an enthalpy rise across stage 2 delta H2, which is equal to U2 square. Okay, as I have already mentioned, both the impeller stages are mounted, have same diameter, and they also have the same rotational speed. That means the tip speed for both the stages are same. Once the tip speed is same, we have seen from our equations that the work of compression for each stage should remain same. Okay, that means delta H1, that means the work of compression or enthalpy rise across impeller 1 should be same as enthalpy rise across impeller 2, because both of them are equal to U2 square, where U2 is the tip speed. Tip speed is same for both the stages. Okay, but since the total enthalpy rise, that means H exit minus Hi is equal to enthalpy rise across impeller 1 plus enthalpy rise across impeller 2, you find that the total enthalpy rise across the compressor is equal to 2 into enthalpy rise across each stage. Okay, that is what is mentioned here. Enthalpy rise across the compressor, He minus H1 is equal to delta H1 plus delta H2, which is equal to 2 into delta H stage. Now delta H stage is nothing but He minus Hi by 2, and from the given input data, delta H stage is equal to 419.8 minus 398.6 divided by 2, that is equal to 10.6 kilojoule per kg. Okay, and we know that this is equal to U2 square, that means U2 is equal to square root of delta H stage. Since this delta H is in kilojoule per kg, and if you want to find out velocity in meter per second, you have to multiply this into 1000. So U2 is equal to square root of 10.6 into 1000, that is equal to 103 meter per second. So this is the tip speed of both the stages, and we know that tip speed U2 is equal to rotational speed omega in radians per second into the outer radius. Okay, so and we know what is omega. Okay, omega is nothing but 2 pi into rpm by 60. So rpm is given as 3000. So you have to convert that into revolutions per second and multiply that into 2 pi to convert this into radians per second. So 3000 rpm works out to be 100 pi radians per second. So if you substitute this value, you find that the required outer radius is 0.3279 meters, and the required impeller diameter is equal to 2 into R2, that is equal to 0.6558 meter. Okay, so this has to be same for both the stages. This is a simple problem, okay, but it basically outlines the procedure using which you can calculate the pressure rise, or if you given the other pressure rise and all, how to calculate the impeller diameter, etc. Okay. Let me give a homework problem which you can try at home. Before that, let me conclude what we have learned in this lesson. In this lecture, the following topics are discussed: refrigerant capacity and how to control it, surging in centrifugal compressors, effects of operating temperatures and speed on performance, performance comparison with reciprocating compressors, and commercial systems with centrifugal compressor. These are the aspects covered in this lecture. And as I have already mentioned, with this lecture I complete my talk on compressors. Okay. So before I leave off, let me give a homework problem. The problem is like this: a backward curved centrifugal compressor is to compress refrigerant R134A. The diameter of the impeller is 0.6 meter and the blade angle is 60 degrees. So this is not a radial curved blade, so you have to keep that in mind. And the peripheral area is given to be 0.002 meter square and the flow coefficient is 0.5. What is flow coefficient? Flow coefficient is nothing but the ratio, as I have already mentioned, is the ratio of the normal component of velocity at the impeller exit to the tip speed of the impeller. Okay, so this is the definition of flow coefficient, that is as per the velocity diagram, this is the ratio of Vn2 to U2. Okay, the flow coefficient is given as 0.5. If the pressure and temperature of refrigerant at the exit of the impeller are found to be 7.702 bar and 40 degree centigrade respectively, find the specific work and power input to the compressor. The impeller rotates at 9000 rpm, the slip factor may be taken as 0.9, the refrigerant may be assumed to enter the impeller axially. Okay. The slip factor, if you remember, I have defined as the actual tangential component of velocity at the exit to the tangential velocity component in the absence of eddy losses or in the absence of any slip. Okay. So this is the definition of slip factor, that means Vt2 actual divided by Vt2 in the absence of eddy losses. Okay. So this is the information given. From this information you have to find out what is the power input and the specific work to the compressor. What you have to do is, you have to, from the given information, first you have to find out what is the tip speed, and from the tip speed you have to find out what is the tangential component. Okay, because once you know the tip speed, you know the normal component, and since the beta is given, you can find out what is the tangential component when there is no slip. Okay, and once you find this, you can find out what is the tangential component with slip, because the slip factor is given. Once you know this one, you can easily find out what is the work of compression and what is the power input. I will give you the answers to this problem in the next class. And let me also give you a few objective type questions. The first question is, in a centrifugal compressor, as refrigerant flows through the impeller blade passages, what happens? For A, its kinetic energy increases, B, its static pressure increases, C, stagnation enthalpy increases, and D, all of the above. And second question is, the purpose of a diffuser in a centrifugal compressor is to convert static pressure into kinetic energy, convert kinetic energy into static pressure, or decrease stagnation enthalpy, or D, none of the above. Okay. And third question is, if the blade angle beta is greater than 90 degrees, it is A, forward curved blade, B, backward curved blade, C, radial curved blade, D, aerofoil type blade. 4. As the blade angle beta increases, A, specific work of compression and pressure ratio increase, B, specific work of compression increases and pressure ratio decreases, C, specific work of compression decreases and pressure ratio increases, and D, none of the above. So question number 5, surging in centrifugal compressors is likely to occur when condenser temperature is low and evaporator temperature is high, B, both condenser and evaporator temperatures are high, C, condenser temperature is high and evaporator temperature is low, D, none of the above. Question number 6, compared to reciprocating compressor, the performance of centrifugal compressor is more sensitive to speed of the compressor, B, evaporator temperature, C, condenser temperature, and D, all of the above. And question number 7, centrifugal compressors are more suitable for large refrigeration capacity applications, small refrigeration capacity applications, C, medium capacity applications, and D, all of the above. And the last question, irreversibilities in centrifugal compressors are mainly due to heat transfer effects, viscous shear forces, pressure drops across valves, and all of the above. Okay, I will give the answers to these questions in the next class. Thank you.